We've created the solid model in the previous video in SolidWorks, so now we can use that and try and create the flow analysis domain in this video. And in this video, I'll show you how to turn that solid model into an external flow example, and then we'll play around with looking at it at different angles of attack and try and compare that to the results that we should expect to get. So I'm just going to fire up flow simulation. We can start the wizard, and we'll call this airfoil NACA 001. And happy with the units. Now, this is going to be external flow, so we'll choose that. We'll exclude cavities and we'll exclude the internal space. There aren't any cavities in this model, but we're just making it simple. Now, I'm going to, just for the fun of it, I'm going to use water. So this will be a hydrofoil. And you can see that, so we're using water as the liquid, and the flow type we're going to pick is laminar and turbulent. Now we could, if we knew the flow rate, the velocity was going to be very slow and we weren't going to reach turbulent conditions, we could use laminar only. We can't use turbulent only because this is a wing, and we know from fluids that the first bit of the leading edge in an airfoil is going to be laminar until the turbulent boundary layer forms. So we need to be able to model both laminar and turbulent conditions. I'm not going to include cavitation in my model. I probably should, but I won't in this case. Roughness, I'm going to keep it smooth. And I'm going to use an X direction velocity. So this will be the speed of the water going past my hydrofoil of 1 meter per second. And you can see that the speed showed, whoops, down here, what it is. We can also look at some turbulence parameters. You can play around with these, but you're going to need to learn a little bit about turbulence theory to know what values to pick. We'll just leave it at the default. There. So what we've got now is a wing, and there what we're seeing is the simulation region, the computational domain. Now this computational domain, it's pretty small. So our wind speed is going from left to right, but our wing is taking up an awful lot of that box. We could leave it like this. We might want to increase its size, but well, we'll try and run this and see what we get. The other thing that you notice is that the ends are within the model, which means that there's a gap between the computational space and the end of the wings. And I want this as best as possible to be a two-dimensional representation. So I'm just going to move that to 0, which is where my airfoil, my hydrofoil starts. And I'm going to move this to 1 meter. So now we should have a foil which is reasonably close to an ideal one. It's 10 times long as it is in chord, and that's our model. Now you'll notice that a typical wing, if the wind is coming from the left or the aircraft or hydrofoil is going to the right, there should be some angle of attack. but you'll see I've made this wing so there's 0 angle of attack. And I can do the simulation like this. Now, what I've done previous to this this video is I have done a number of angles of this model. So I did do the 0 angle one, but I'm going to show you not the 0 angle. I want to start off by actually showing you only one run, but we'll talk about the rest of them. And so I'm going to, let's see, have a look back at my model. And the, whoop, seem to be off the screen there. There it is. So I want to actually run several studies of this this hydrofoil at multiple angles of attack. So I'm going to, before I get started too much, insert another feature change. And I'm going to use the move copy feature. The body I will move is that one. And I'm not going to copy it. I want to rotate it. And I'm going to rotate it about the origin 0, 0, 0. And in the Z direction, I'm going to just see, well, if I do that, it will go down. So I'm going to rotate it. I'll just pick 10 degrees. So now I have an airfoil where it's got an angle of attack as you would expect for an airfoil that's working at 10 degrees. And I can go back to the flow simulation by clicking this button and finish some of the conditions here. Boundary conditions. I can look at some boundary conditions, and I'll pick boundary conditions at the wall. I'll make that a real wall. And so that makes for the boundary layer to behave properly. I can set some goals. And I'm going to use what are called surface goals. And the surface goals I'm interested in, I'd like to compare the lift force and the drag force. So I'd like to compare the force in the X direction and the force in the Y direction in my simulation. And I have to select that surface. So you'll see that I've got these surface goals 1 and 2 now, and you'll be able to monitor those as the simulation runs. So next step is meshing, and I can look at the mesh settings. First of all, I'll show the mesh, and you can see that my basic mesh is pretty coarse. There's an awful lot of points sideways, and I think that this is going to be a really long simulation if I leave it like that. So because I only have limited computer horsepower, as do you, I'm going to have to modify this. If I right click and edit my definition, I'm going to dial this back to a coarser grid. And I think I'll try to have my mesh scaled closer to the body, something that looks reasonable. And that will at least save some computational time. It's not a hugely detailed mesh. In fact, it's relatively coarse, but we'll give that a try. And with that, the last thing I want to do is I want to click the calculation control options. Now, one of the things you'll find with with any flow simulation is that it's really easy to create a simulation that has way too many grid points and way too much time to solve. So I'm going to limit the number of iterations. I'm going to set mine for 100. I'm also going to limit the calculation time. I do not want my calculation running for very long, so I'm going to limit that to something like 300 seconds. That's a reasonable amount of time. Any longer than that, and I've specified something that will be too hard for an initial try. And that's all the settings that I need. And from here, I can just run. Now the first thing it's doing is setting up the grid and then doing the calculations. You'll see the number of iterations that it goes through. And there, the solver's finished. It tells me it's finished right there. And that was 100 iterations, which was the limit that I set. It would have kept on going, and it took just shy of 2 minutes of CPU time. Now, that was 2 minutes of CPU time. That was longer than that at elapsed time because your CPU and mine are doing other things all the time. So let's see how this result looks. One thing we can look at is the goals and how they proceeded. So if I just look at this plot, I can see that the two goals that I set, and you can see in the first 10 iterations, they were wiggling around quite a bit. And they did stabilize to two different numbers by 80 calculations. And at 100, they were still wiggling around. They were still hadn't stabilized, at least on this scale, so that I could see no difference. But let's just see how that looks. So when you look at the model, nothing much has changed, and that's because the results over here are over here. First thing I want to look at is I want to check what my mesh looked like for that. The mesh gets modified through running, and I'm going to pick I want to pick a mesh on my XY plane. Yes. And you can see that I can drag that mesh anywhere I like. We'll just put it there. I can specify if the mesh is a fixed color, and it will be. And I'd like to make this mesh fairly light colored. I don't want it to be colored by the grid points. There. And so you can see there's an example of what my mesh looks like. It's pretty coarse. But I did have to use an awful lot of grid points horizontally to get this result. I can look at some cut plots. Right click on that and insert a new cut plot. And I'm going to want this cut plot partway along. I'll pick contours and vectors and streamlines. Let's see how that looks. Yeah, the vectors are kind of ugly. You can see that they look a bit like what we'd expect, but let's look at a different cut plot. Let's modify that. We'll have velocity. We'll not have the vectors. We'll just go with streamlines. and we'll color them by pressure. And so you can see from that, well, my color scale is not the nicest, but you can see that the flow lines are going as you'd expect around that wing. Now, one of the things that everybody likes to see are flow trajectories. And we can pick some mesh-based trajectories. And so this would be particles we've seeded in the flow that don't look very interesting. So we'll use these, and pipes are nice sometimes. We've got 20 of them. That usually looks okay. There. Don't like the fact that they're on the end, so I think maybe we'll move that. There, so we've just selected the surface that we want these pipes to go over and under, and they're all on the bottom side. There's some of these snaky ones over here. What's going on with them? Don't really know. And you can play around a lot with making the graphics look okay. And clearly I need to play around a lot with that for this one. The important thing here are the surface parameters, because that's what I was interested in finding. I'm looking for the force . And so you'll see that the force on this surface from my flow is shown over here as 14.9 newtons on the whole airfoil, but an X component, which would be drag, of 3.2 newtons, and a Y component of 14.5 newtons. So with that, I've got a prediction of the lift and drag on this airfoil. There, so our first run of this model, we've got a result. The result was 14.5 newtons of lift and 3.9 newtons of drag. The lift over drag, therefore, is going to be something like 3.7. That's a lot less than the 30 to 40 that we're expecting from looking at the drag curves and lift curves for this particular airfoil. So clearly, we've done the simulation, but the numerical result isn't correct. And yet, looking at the flow, the streamlines, looking at the flow, it looks right. So we need to look at this in more detail.